Hi, I'm Sean Gannon, and this is Minute Math, and today we're learning about related rates.
Minute Math, when you need help you use Minute Math.
We're given this problem right here. Water leaking onto a floor forms a circular pool. The radius of the pool increases at a rate of 4 centimeters per minute. How fast is the area of the pool increasing when the radius is 5 centimeters? Okay, so let's first draw a picture from what we're given here. We're going to start with a circle, right? So I have a circle here. Don't judge my circle. And we know the circle has a radius, right? Every circle does. And that radius is given to us as it's changing at a rate, so that the rate of the radius over time, dr dt, all right, the rate of the radius is 4 centimeters per minute. Okay, so we have 4 centimeters per minute is that rate of the radius going out. Now, we want to find out what happens when the radius is 5 centimeters. They tell us at the end there. So we want to find what happens when it happens that the radius is 5 centimeters. I can fit that in there. Okay. Now, one thing we want to know is, well, the area of a circle. That's important to get here. So area of circle is pi r squared. Okay. All right. So now when we take this related rate, we want to actually derive this formula for the area of a circle with respect to time. Okay, and we're going to get some of the information that we need from there. Okay, and so when we do that, we take the derivative with respect to time, d over dt, of our area, and that's equal to the derivative with respect to time of our other side of the equation, pi r squared right here. Okay. Now, the left-hand side's pretty easy to find. The derivative of the area is, well, with respect to time, is just going to be that dA dt. Okay, pretty easy to find there. Now notice dA dt. They said how fast is the area of the pool increasing at this specific moment. dA dt is what we're looking to find. Okay, so we're on the right track here. The right-hand side, when we derive this with respect to time here, notice that pi is just a constant, so we can take that constant, put it out front. And now we're really deriving r squared with respect to time. Now, the radius here is a kind of a function of time, okay? So when we actually derive this, we have to do a little special thing going on. It's like the chain rule in a way. So we have dA dt is equal to pi, and now using the chain rule, derivative of this we take of r squared, the 2 comes out front, times the inside, that r value, subtract the exponent by 1, so we just have a 1 up there, times the derivative of r with respect to time, which is that dr dt. And now we actually have a pretty good formula. We can plug in what we know. The radius at the moment we're talking about is 5 centimeters. So we have dA dt is equal to pi times 2 times 5, and the units is centimeters, times dr dt, all right, which we know is 4 centimeters per minute. They gave that to us. So we have 4, and its unit is centimeters per minute, right there. So we multiply all this out, and we have 2 times 5 times 4, and that's going to give us our 40, and then the pi, right? So we have dA dt here is equal to 40 pi, and that's our units, centimeters times centimeters per minute is centimeters squared per minute, and that actually works as we're talking about how the rate of an area changes. So that dA dt, what does that equal? Well, that's that 40 pi centimeters squared per minute, not meter, per minute, right there. All right, so 40 pi centimeters squared per minute is our final answer. I hope this video was helpful for you, and if it was, please subscribe to this YouTube channel and like this video. This helps us make more free math lessons for you and for everyone else. So as always, thanks for watching.
Minute Math, when you need help you use Minute Math.